Very good afternoon to all. Welcome you all for the series lectures of the digital signal processing. In the previous sessions, we have undergone the unit 4, the design of digital FIR filter. Under that, we solved the impulse invariant method to transfer h of s, that is analog transfer function, to h of z, that is digital transfer functions, right? So now in this class we will move on to the next method, that is backward difference method or numerical approximation method. So I'll start sharing my screen. Kindly acknowledge the same. Okay, we were discussing about the design of digital IIR filter. So now under that we will go for the next approximation method, that is numerical solution to the differential equations, or in other way we also call it as approximation of derivatives. Dear students, kindly note this point. So, numerical solution to the differential equation, which means that we are trying to express, or we have a input and output in the form of differential equation, t by dt form. That's where we call it as a differential equation, the first important point. And we try to approximate that derivatives, so that in turn I try to write my equation in the form of h of z. So, here moving further, so the fundamental method that we try to adapt here is the backward difference method, or we also call it as the solution for differential equation. Yet another way of describing the transfer function in the form of linear constant coefficient differential equations. You might have studied this in your third semester, signals and systems. That is representation of differential equations and the solving for the differential equations, which means that the LTI systems, linear time invariant systems, can be represented in the form of differential equations and difference equations. For such equations, we derived the output, or we derived the solution in the form of natural form and complete solution, right? Uh, in that way, if I want to represent, then I will be representing my equation in this form, where ak and bk are the coefficients, where y of t is my output and x of t is the input. So this is where a series of summation values y of t, y for d1 by dt of single order, or if it is second order, then d square y by dt square, and similarly if the input is of second order, d square x of by dt square, a kind of thing we already have a familiar of these kind of equations, that what we have represented in our signals and systems to represent a LTI system. That's why we call it as the linear constant coefficients, where AK and BK are the coefficients of the differential equations, right? So this is how we represent our LTI system. If you remember, the LTI system representations in the form of differential equation and difference equations, right? Difference equations. Again, differential equations for continuous time and difference equation for discrete time, right? So once we obtain the difference equations, So later on for difference equation it is very easy for me to apply z transform because difference equations represent by discrete time signals. The point is I need to convert this differential equations. So now the very important point is the differential equations which are in the form of d by dt form. So this is the differential equation. Convert this into difference equations. Convert this into difference equations. How do you convert? So in the form of y of n plus y of n minus 1, right? So this is how we try to represent our difference equations. Once we obtain the difference equations, then it is very easy for us to represent these or to convert these difference equation into z transform, right? Now what is the procedure or what is the technique that we have to convert the differential equation into difference equation? Converting a differential equation to difference equation, that is then one of the method or one of the technique that what we have learned in our mathematics is fundamental mathematics is Newton backward difference method, and we also have Newton forward difference method, right? So basically this forward difference method and backward difference method is used to represent any continuous time or any continuous function into the form of discrete signals or discrete equations. So that's where we try to represent as a sample. So this is how we try to represent any differential equation. The main principle approximate is the finite differences. Where consider an example. If I have dy by dt, which is varying with respect to time t, and we sample this t at t equal to nt, and this can be represented in the form of Newton backward difference method in this way. So where delta of 1 represent the first order because this is dy by dt or to the power of 1. So it is a first order equation. So further this can be converted into this form since it is a first order. Then how do we represent by Newton's backward difference method? Y of n minus y of n minus 1 divided by t. So that we call it as the equation 1. Equation 1 is called as approximation of differential equation by backward difference. That's it. Okay. Now, similarly, we have these equations on the left hand side and on the right hand side. So what is this right hand side? So input x of t, right? So this is our input and this is our output equation. So y of t represents our output and obviously x of t represents my input here, right? Now how do you write this uh, differential equations or in the form of difference equation? Just a minute. Okay. Let me call this for the timing. I'll call this as equation number 2. Equation 1 already represented in the previous slide. Now, the LHS of this equation number 2, if I take only the LHS part, LHS of equation number 2, if I try to represent in the difference equation form, so this can be written as so summation k runs from 0 to n ak d by dt of kth order. So this is the kth order. Y of t is equal to it where we try to sample this t for n into t times, then this can be represented as, so it is again a summation. I'll keep that summation, I don't disturb that. So this will be even the difference equation will be moving with the k equal to 0 to n, and the coefficients remain same, no change in it, but only d by dt is going to be changed. So that is if single order we try to represent this as y of n, right? but it is kth order. So this is kth equation. This is how we try to represent. So let me take it as equation number 3. And similarly, the RHS of the second equation can be represented as, so that is k equal to 0 to n, bk is the coefficient, d by dt of kth order, x of t, where t is sampled at nt, and this is going to be represented in this form, that is k equal to 0 to n bk, backward difference method, that is y of, yeah, sorry, x of, yeah, x of, yeah, fine. So let me call this as equation 4. If I combined these equation 4 with respect to LHS and RHS, then I have a equation, or I can write this equation in this form, that is AK delta of k y of n inverse delta, it is actually, is equal to k runs from 0 to n bk inverse delta of k, that is backward difference, that's why we write it as inverse delta x of n. This is how we represent the conversion of equation 2 in the form of difference equations, that is difference equation, that is represented by equation number 5. So let us call this as equation number 5. So this is how we try to represent here. Now, but what is our objective? Now, what we did here from equation 2 to equation 5, what indicates? So that is, so here the equation 2 was continuous time equation, right? Differential equation. Now, if you observe this equation 5, this represent my discrete time signal or discrete time function, I can call it as, right? So where the continuous time function is represented in the form of discrete time function. So this is first time major step that what we are supposed to do. Then once we have this difference discrete signal, and later on it is very easy for me to convert it into h or h of z. So our main objective is what? Our objective is to obtain h of z, to obtain h of z, right? So from the above equation, that is z transform, see, if I write, note this, the z transform of the inverse delta of y of n is given by, is given by is given by, so that is I need to write the y of n. So what is y of n here? Basically this is nothing but y of n minus y of n minus 1, right? This is how. And if I take this sampling time, then this is by t. So now what is to be done? I need to obtain the z transform of this. So that is z transform of this. So on the left hand side, a z transform of this. There, let me write zt here. Okay, zt. Now how do you write the z transform for this function? This is very simple. 1 by t is a constant. I will take it outside. So y of n z transform is y of z, right? So y of n z transform is y of z, and y of n minus 1 z transform is y of z. So delay by 1 unit, so that is going to be represented as z inverse. So this is zt of this, right? Now minus y of z into z inverse. So now you got it, how to write the z domain from the difference equation, right? So this point we will adapt in our equation. So this is the very important point. So I'll take this as reference for converting my equation 5, that is this equation, in the form of z transform. So that we write that. So if it is to be written for kth value, or kth order. So let me write this for kth order, that is y of n for kth order. Z transform of this can be written as 1 by t as it is. Here, moreover, I can take y of z as a common factor, like 1 by t. Y of z, if I take it as a common factor, then it is 1 minus z inverse, right? Now, if this is for first order, now for the kth order, this will be like 1 by t y of z, okay, 1 by z inverse of kth order. So this is how we usually represent this, right? And so even t is to be under this kth, because for all the k values, for all the k values, t will be varying, right? So this is how we represent for the kth order. Oh, okay. So I'm trying to extend this kth order to equation 5. So similarly, equation 5 can be represented as k runs from 0 to n ak 1 minus z inverse by t whole to the power of k y of z, that is left hand side of equation number 5. So left hand side of equation number 5. So this is the equation number 5 here. This I am trying to represent with a z transform, equivalent z transform of y of n, delta of k to y of n. And similarly on the RHS side, so I am trying to apply the z transform for delta of k x of n. So now that is how we try to represent here. Now if I take x of z by y of z, uh, output by input, I'm sorry, here it is y of z by x of z I need to write. So this gives me h of z. Fine. So y of z by x of z. Y of z, I keep it here as it is. I take it to the denominator x of z. So y of z by x of z can be rewritten as, so y of z divided by x of z. So what we're going to get in the numerator? What is the numerator value here? So that is summation bk 1 int. So that is summation k runs from 0 to n bk, right, 1 minus z inverse by t whole to the power of k whole divided by summation k runs from 0 to n ak 1 minus z inverse by t whole to the power of k. So this is what the equations for, let me call this as equation number 6. What is this? This is nothing but h of z. Fine. Now coming back to our differential equation from equation number 1. I'll take this equation once again for the comparison. So now I can write this y of t by x of t. If I want to write, then how do I write this? That is h of s. It is nothing but, right? H of s is nothing but y of s by x of s. So this is nothing but summation k runs from 0 to n bk, right? So here it was d by dt. If you look at this equation, it was d by dt. D by dt with respect to anything what I can write. So this is nothing but S domain. I convert this x of t and y of t. So I am trying to write this x of t, y of t by x of t as in the S domain, that is y of s by x of s. I am trying to shift a time domain to frequency domain. So that is how I write y of s by x of s. And how do you write the d by dt of that? So that is simply the s we try to represent, right? This is how I try to represent this as s to the power of k. A d by dt is going to be represented as s to the power of k. Summation k runs from 0 to n, and this is ak s to the power of k, right? So this is how it is going to be represented as. So where AK and BK are filter coefficients, we call it as, or simply a coefficients. Fine. Now just observe equation number 6 and equation number 7. So this is Z domain, this is S domain. So when I map S to Z domain, what is S is equal to here? So in S domain, S is equal to, if you observe this, everything is same. S is represented by 1 minus Z inverse divided by T. That's it. So wherever you get S, if I want to move from S domain to Z domain, S domain to Z domain, replace S by 1 minus Z inverse divided by T, and this method we call it as what? Backward difference method. Backward difference method. So in the previous case, in the impulse invariance method, what we did? We applied a technique. We had H of S Mukantra. We went back by taking inverse Laplace transform and we got H of T. Then we sampled that H of T, and later on we applied, we sampled H of T, we obtained Hn, and for this Hn we applied Z transform to obtain H of Z. Now this was the transformation technique that we adapted in impulse invariance method. But here in this case, I am trying to represent the system in the form of differential equations, and differential equations, the Laplace of that differential equations output to input is going to be represented in this fashion. And later on I adopted the backward difference method technique in order to solve the differential equation to difference equation, that is converting a differential equations, converting a differential equation to difference equation. So what is the meaning of this? Converting a differential equation, conversion of differential equation to difference equation, which is nothing but a signal was in continuous time, it is transformed to discrete time. Once we have a discrete time equation, applies that transform to obtain h of z. That's it. So in that scenario, where you have a s in h of s, if you apply or if you replace it by 1 minus z inverse divided by t, then it indicates that this is a backward difference technique. We are solving the roots of the characteristic equation by adapting the backward difference method technique. Is this clear, students? So now what is to be replaced? So now this is s and z. How do you map this? So there's in s domain, replace this by t, and what about z? Z, so that is equal to s into t equal to 1 minus z inverse, right? If you transfer this t over to the left hand side, and therefore st equal to 1 minus 1 by z, and s into t equal to z minus 1 by z. So therefore if you solve this for z, we will going to get if you solve this for z, we will going to get z is equal to 1 divided by 1 minus s into t. Um, what is the meaning of z in case of this? Now, because I need to map a frequency, right? I have a poles and zeros in the s plane. So I need to map it on the z plane, the poles and zeros. That is which I need to ensure that is all the left hand side poles and zeros will lie within the unit circle because to ensure the stability of the system, right? So similarly, this is the relationship between. So this equation gives. Let me call this as equation number 8. Okay, and this is equation number 9. Equation number 8 and equation number 9 gives me the systematic relationship between z domain and s domain. That is relationship between s domain and l z domain. Fine. Okay. Any doubts? I'll just the chat room. So our next topic is on mapping of analog frequency, mapping of analog frequency to digital frequency. Fine. Okay. Now we already have this digital frequency, that is uh, z equal to z equal to 1 minus 1 by 1 by 1 minus st. What is s equal to? S is nothing but a hidden frequency that is consisting of, that is S equal to j omega. Right? Now put this here 1 minus, put S equal to j omega. Now you got this frequency term. So you can obtain the relationship between a frequency component in the digital domain. Right? Now since in the denominator I have a imaginary value, I should remove this. What we should do? We must go for rationalization of the denominator. So let me go for rationalize the denominator. So rationalize the denominator here. So if I rationalize, and z is equal to 1 by 1 minus j omega t into 1 plus j omega t divided by 1 plus j omega t, and this gives me 1 plus j omega t in the numerator, and in the denominator I'm going to get 1 plus. So since j into j is j square is minus 1, minus into minus gives me plus, so omega square and t square. Fine. So this is how I'm going to get. But till now I'm not able to get the frequency component exactly. How do you get that frequency component? Because I need to map from S domain to Z domain for various frequency values. Right. So here there is one technique that what we try to adapt here. Look at this in the denominator. We try to map this, or we can rewrite this as, so if there exists a term, let me take here in the numerator, you I have a j term. In the numerator I have a j term. So again, which is in the form of, let me take this separately, 1 by j omega t is going to be it is in the form of x plus iy, right now. Now I can write this as square root of x square plus y square in, into e to the power of j theta. Right, this is how I can rewrite if I want to obtain this magnitude, because I need only magnitude of this. So therefore, where theta is equal to what? What about theta? Theta is nothing but tan inverse of y by x. So from the basic trigonometry, we know this. So therefore, the numerator can be represented as the numerator term, that is 1 plus j omega t, can be represented in this form, that is square root of x is 1 plus y square is nothing but omega square t square, and into e to the power of j theta into e to the power of j. Theta is tan inverse of y by x, and y by x is nothing but omega t divided by 1. Fine. So this I try to represent here, z equal to numerator. So I made a small homework here. So in order to represent this 1 plus j omega t as under this root 1 plus omega square t square e to the power of j theta. Theta is nothing but tan inverse of b by a or y by x. So that is omega square t square divided by 1 plus omega square t square. You might be knowing, you might be surprised why I am doing all this. So this will help me to map the frequency components onto the z domain. So this will help you out. Wait for a few minutes. We will going to get the usage of this equation. Right now I will call this as equation number 10. I think 10. Yeah, equation number 10. So after this, we need to ensure that whether this particular equation or pole and zero, whatever we try to plot, pole to zero mapping should be lie within the unit circle. That is one of the criteria to ensure the signal is what stable or not. So let me go for the second case here. Mapping of mapping of pole 0 on z domain. Okay, so consider this equation once again. Equation z is equal to, because I need this equation basically, j omega t divided by 1 plus omega square t square. So this I can rewrite it as 1 divided by 1 plus omega square t square plus j times omega t divided by 1 plus omega square t square. Fine. Entire this value, I consider this as x, and entire this value I consider this as y. Okay, so just observe carefully. Z is equals to x plus jy. Now we'll do a small exercise so that which helps me to understand the pole zero model, because of this the obtained the z value. Very important observation that what we are supposed to do. So I just will go for an important observation here. Now this mathematics is very beautifully designed, and we take those basics of all our trigonometric relations and the equations, so that it helps us to understand more clearly. So just I have x and y. So let me go for taking this x square plus y square. What is x? So this is x square plus y square, that is 1 plus omega square t square whole square plus omega t omega square t square divided by 1 plus omega square t square whole square. Okay, now if you see this, then what we get? 1 plus omega square t square divided by 1 plus omega square t square whole square. It will going to cancel this And now I can write this as 1 plus omega square t square. What is this 1 plus omega square t square? Which is nothing but a x, right? So this is nothing but, look at this x. So when I perform x square plus y square, I am getting once again x. What is this equation? What is this equation? Can anyone tell me? So once again, I request to concentrate this equation. So this is one equation. So from 9 we took this equation here. So in this, look at this. This is x and this is y. If you take x square of that and if you take y square of this and you will going to get x, you are again going to get this equation. This means that the equation number, okay, sorry, 11. Equation 11 indicates what? It indicates the circle. So this z is equal to, this is going to give me a circle equation. That's it. A circle equation with radius with r equal to 1 by 2 and the coordinate of x comma y is equal to 1 by 2 comma 0. Y coordinate is 0. You don't have a y coordinate here. Y coordinate is totally 0 and x coordinate is going to be 1 by 2. So if you want, I'll just show you how to do. X square plus y square is equal to x. We have just add 1 by 4 on both the sides because I need x minus h the whole square plus y minus h the whole square, the distance formula, that is r square. So that is what in this form I need. So in that fashion, if I want, so x square plus y square plus 1 by 4 is equal to x plus 1 by 4. You keep this 1 by 4 on the right hand side and you transfer this x to the left hand side. Okay, then accordingly you will going to get a minus b whole square formula. So this is minus that is 1 by 4 minus x. I'll do it here plus I take this one side and y square. So this is equal to 1 by 4. Now I can write this as 1 by 2 whole square. Okay. So look at this. If you observe carefully, so this is a minus b whole square formula. So x minus 1 by 2 whole square I can write plus y minus 0 whole square I can write. So this is 1 by 2. So this is my circle's equation. This is my circle equation. Fine. So what happens here? H is off, which is the distance from a. This is a circle. So this is at 1 by 2. Okay, this is 1 by 2. The h and this h represent the the distance of the circumference from the radius, from the center of the circle. Okay. uh, y-axis is 0 totally. So the it is r equal to 1 by 2 and this is 1 by 2 comma 0, the distance. Okay. This is how I call this equation x square plus y square. This is equation. See, my concentration here is z equal to 1 plus j omega t divided by 1 plus j omega square t square is nothing but it is giving me a circle equation. That's it. It is giving me circle equation with radius of 1 by 2, which means that the z which is supposed to be mapped within the unit circle, within the unit circle z plane ಮೇಲೆ one unit circle ಮೇಲೆ ಆಗಬೇಕಾಗಿತ್ತು. So more than a unit circle, it is representing with radius of half. So this is the entire frequency of S plane. Entire frequency of S plane is mapped well within the radius of 1 by 2 within the Z plane. So obviously the system is stable. system is stable, no doubt at all, right? So this is the importance and beauty of this mathematics hidden in the differential equations and difference equations, and then to z transform, and then we are checking that the z value is stable or not. Okay, so this is the very important point here. Now I need to map this to conclude. Ultimately, I need to map. So what is to be done? So for conclusion, right? So S is equal to j omega. The entire frequency mapping x is mapped on the z plane, on the z plane with center at 1 by 2 comma 0, and the radius is 1 by 2. So this is a conclusion, and we'll try to map with the same here, so with different frequencies. So let me consider that z with omega equal to 0, with omega equal to 0, let me take the value. So what we see here, z is equal to e to the power of j tan inverse of, so this equation I'm taking because I need to map. So this is a frequency. What frequency? Digital frequency. Okay, omega analog frequency to digital frequency we are trying to move. So here I should apply various frequencies of s plane. See to that the value of z will lie within unit circle or not, that I should check. So that's where I'm considering this e to the power of tan inverse of omega t divided by square root of 1 plus whole square, right? 1 plus omega square plus this square, right? So okay, why I take this as, look at this. If I take this as whole to the power of 1 by 2, here that is 1. Okay, if you subtract, or if you go for that algebraic equation, I can subtract, I can take it to the numerator, and this is 1 by 2 minus 1. Once again, we're going to get minus 1 by 2, so that I get this term in the denominator. So that's why I take this in the term in the denominator. That's it. So now put omega equal to 0 first. With omega equal to 0. So what we get? Z value. Z equal to j into tan inverse of 0. What is tan inverse of 0 here? So tan inverse of 0. Tan 0 is 0, right? So which is nothing but e to the power of j 0. Okay. Then divided by 1 plus 0. The frequency is 0. So once again it is 0. So this is 1 divided by 1 with omega equal to 0 in S domain. The Z frequency lies at 1. Okay. Now with the S plane, in the S plane, if omega is lying somewhere else infinity, maximum frequency if I consider, then e to the power of j tan inverse of infinity we will going to get. When do we get, what is the value of tan infinity, tan inverse of infinity, and divided by 1 plus infinity. So what is tan inverse of infinity? What is tan inverse of infinity? Which is 1, right? Which is 1, and in the denominator, look at the denominator term. This is 1 plus infinity. If I take 1 plus infinity, if I add anything to the huge value by 1, then it itself is a huge value. So therefore this is infinity itself, and in the denominator I can replace with the infinity itself, and this becomes 1 by infinity, which means that if you are trying to map a very huge frequency, very high frequency in the S plane, that in the Z plane it maps to 0 frequency. That is what the meaning here. And omega equal to 1 by t and minus 1 by t. I should check that. So if you remember carefully, these are the different values that we have checked in the impulse invariance method also. And e to the power of j tan inverse of 1 by t into t, okay, divided by 1 plus 1 by t square into t square, right? So here I am trying to put 1 by t, so since it is whole square, 1 by t square into t square, so this and this get cancels. This I am going to get e to the power of tan inverse of 1 divided by square root of 1 plus 1, it is 2. Now what is tan inverse of 1? It is nothing but 45 degree, right? It is nothing but 45 degree. Here it is e to the power of j 45 divided by root 2. Now coming back, what is e to the power of j 45? J 45 can be written as pi by 4, right? So this is nothing but cos pi by 4 plus j pi by 4 sin pi by 4. What is the value of cos pi by 4 plus j sin pi by 4? What's the value? 1 by root 2 plus j times 1 by root 2, right? So therefore z with omega equal to 1 by t, the value of z is equal to 1 by root 2 plus j times 1 by root 2 divided by root 2. Simplify this, I can again make sure that 1 by root 2 divided by root 2, that is 1 by 2 whole square, that is nothing but 1 by 2 plus j times 1 by 2 I am going to get, so which is nothing but 0.5 plus j 0.5. Now let us map this onto the from S plane to Z plane, okay? So now this is, so here is my S plane for my all the system stable system poles lies within this range. That is, one is omega equal to 1 by t, infinity minus infinity, and somewhere else here minus 1 by t and 0, okay. uh, the circle unit, it is not unit radius, now it is half radius. So this is the z plane, okay, unit radius. But when I transfer my value from S plane to Z plane, then because of radius is half at what we observed, I'm going to get all the values well within this range. Let me take a different color here. Okay, now this is radius. So this is radius of 1 and this will be radius of half, right? And the center lies at 1 by 2 comma 0. Fine. Okay. Now what is the value of omega with 0? First value, it is z equal to 1. So which means that this value is going to be mapped on my z plane at here, at this point. Now once again, for infinity it is 0. So for plus infinity and for minus infinity it is mapping to 0 value. So where the 0 appears here. So that is 0, and the if you take minus infinity or plus infinity, it is 0. And let me take another color. Now look at this 1 by t. What is the value of 1 by t? That is half and half. 1.1 by 2 and what is that? This is somewhere else here I am going to get zero point 0.5 plus j times zero point 0.5, right? So this is from here zero point 0.5 and j 0.5, zero point 0.5 plus j 0.5, and complex conjugate I'm going to get when it is minus 1 by t, right? It has to be complex conjugate, so minus j 0.5. I think it is visible or not. So this is here. Okay, so this is the point that is going to be mapped. So for this I'll try to map it here, and for this I will try to map it here. Okay, this is how we try to map the entire frequencies of S plane onto the Z plane, and now this is my the frequency range. This is my frequency range. All the frequencies will go into line, that is from ranging omega equal to 1 by t here, and omega equal to minus 1 by t here, and this point is omega equal to 0. So hence all frequencies of S plane, what is the maximum frequency f is equal to infinity, is also mapped, including infinity, is also mapped on z plane, within unit circle, within unit circle. So hence the system is stable. So this is all about the numerical solution for differential equations. Any doubts here? I hope you are not sleeping. Okay, so this is the main intention here. If you have any doubts, please let me have a small discussion, so that I could able to clear your doubts right now. I'll just pause the video and stop the recording.